Welcome back to Practical PyTorch. You write a plus B and think one step. It is not one step. It is a lookup that ends in a compiled kernel. We follow that one line all the way down. Then we measure what the lookup costs. Every number comes from one GPU, an NVIDIA L4. You write a plus B and think one step. It is not. That one line is a lookup. It ends in a compiled kernel. A plus B does not name a function. It names an op. PyTorch looks up which kernel should answer it. The choice depends on where the data lives, its type, and whether it needs gradients. We follow one Python line all the way down to the kernel it launches. Then we measure what the lookup costs. This video has 3 parts. First, the dispatch path. We follow one Python line down to one kernel launch. Second, one line, different kernels. Device and dtype each pick a different A plus B kernel. Third, the fixed cost. The lookup is a set price you pay per op. Part 1. The dispatch path. Let's follow one Python line down to a single kernel. At the top of the stack is your code. A plus B, this is the same stack from the first lesson. Nothing has run yet. This is just the line you wrote. Everything below is still waiting. Follow the arrow down from the line. The plus sign resolves to an op. The op is named add. It is an entry in PyTorch's table of operations. The op names the work. It is not yet the code that runs. The op flows down this arrow into the dispatcher. The dispatcher chooses the kernel. It does not run the math itself. It looks up which compiled kernel to call. It reads 3 keys. The first key is the device. That is where the data lives, CPU or GPU. The second key is the dtype. That is the number type, like float32 or float16. The third key is autograd. That asks whether the op needs gradients. The 3 keys point down this arrow to one box. They select exactly one compiled kernel. It is the CUDA float32 add. That kernel is the code that finally does the arithmetic. The whole path is now solid. One more arrow leaves the kernel box. The chosen kernel is CUDA code. It does not run inside Python. It is handed off to run on the GPU. The next slide picks up that handoff. The handoff lands here. This is the same host and device picture from the tensor lesson. The chosen kernel runs on the device. It works on data that lives in VRAM, the device's own memory. And it is reached across the bus, the link back to the host. Part 2. One line, different kernels. The same A plus B can reach several kernels. We run the same add 4 ways. First, both tensors sit on the CPU in float32. Next, we move both to CUDA and add again. Same line, still float32. This line adds in half precision, float16 on CUDA. This last line gives one operand gradients. The syntax A plus B never changes. Only the 3 keys move. Read the table. The op name is add on every row, but the backend flips from CPU to CUDA with the device. The dtype column shows float16 against float32. The last row adds an autograd node, add backward 0. So one line of Python reached 3 different kernels. Device and dtype each picked a different add kernel. The 4th case needs gradients. It reuses the CUDA float32 kernel. It just adds an autograd node for the backward pass. 4 dispatch outcomes, 3 kernels. Every value is from the L4 log. Part 3, the fixed cost. Every lookup charges a small price and you pay it per op. A common belief says the GPU does the math, so the Python around each op is free. It is not free. The dispatch lookup we just walked is a fixed cost. You pay it per op. The lookup runs on every single call. A loop of thousands of tiny ops pays that cost thousands of times. It can be slow even on the fastest GPU. The work per op is smaller than the overhead. Fixing that is a later lesson in this playlist. We measure the overhead directly. We add a tiny one-element tensor. The math is almost nothing, so the reading is almost pure dispatch. The median over 200 runs is about 27 microseconds. About 27 microseconds per op here. That is a floor you pay whatever the op is. It is tiny once, but a loop of thousands of tiny ops turns it into the bottleneck. Batching those ops into one is a later lesson in this playlist. One Python line, a plus b, resolves to an op. That is a name in a table, not a function. The dispatcher picks the kernel by 3 keys. Those are device, dtype, and autograd. The chosen kernel launches on the chosen device, CPU or GPU. One line can reach one or more kernels. That lookup is a fixed cost per op, about 27 microseconds here. It is cheap once, costly across thousands of tiny ops. Your turn. The same line A plus B runs once on CPU float 32. It runs once on CUDA float 16. How many different kernels can that one line reach? Pause and think. Okay, here it is. At least 2. The dispatcher keys on device and dtype. So a CPU add and a CUDA half add are 2 different kernels. They are reached through the same Python syntax. Change the keys and you change the kernel. You now know what one op does. It is a lookup keyed on device, dtype, and autograd. It ends in a kernel launch. Next comes the price of moving data across the bus. That move is the slowest thing in the room, and beginners cross it in a loop.